Okay, we now look at the case, or at least the relationship between the Lagrangian of a differential equation and a conserved quantity. So if we have a differential equation, so consider a differential equation. This is an ordinary differential equation. I'm using the wrong notation. E of x, y dashed, y double dashed equal to 0. Suppose that is a differential equation. Then we said L is a Lagrangian if the Euler Lagrange equation, if E of L equals 0 implies the differential equation. Let's give the differential equation a name, star. Implies star. That means EL equals 0. That's curly L equal to E equal to 0. Let me say that again. That is, if EL equal to 0 is equivalent to the equation star. And also, if I is the first integral, then we have that the total derivative with respect to x of I equal to 0 implies the differential equation. So in this case then, this conservation law for some I is equivalent to star. So there's two aspects here. There's the Lagrangian that comes from the Euler Lagrange operator, and there's the first integral that comes from a conservation law. So there's two aspects. We will now show that there's in fact a relationship between the notion of a Lagrangian of a differential equation and a first integral of the differential equation. And we will again restrict ourselves to second order ordinary differential equations. Okay, let's just go back to an example that we always seem to consider, and that is the free particle equation, the simplest case of y double dashed equal to 0. You may recall where we showed that if L is equal to a half y dash squared, then E of L equal to 0 implies y double dashed equal to 0. And importantly, the factor, let's get to that just now. And if L star equals, in one of the previous notes we've shown that, is equal to a half y dash squared minus 1/6 x y dashed cubed, then if we did the Euler operator on this function L star, then this equation implies y double dashed equal to 0, in which case L star is also a Lagrangian of the free particle differential equation given by y double dashed equal to 0, that equation there. But in the second case, before we concluded that y double dashed equal to 0, we had a factor, a non-trivial, non-constant factor given by y minus xy dashed, or xy dashed minus y. If you turn back to your previous notes, you'll find that we showed that for this Lagrangian L star, we had EL equal to 0 given by that, from which we then implied that y double dashed equals 0 and conclude that L star is a second Lagrangian, and there are in fact many more Lagrangians. In the first case, for the Lagrangian L equal to, for that Lagrangian, we got the factor, very simply factor constant, or in particular terms we got the factor 1 in front of that. So here the factor was a constant, which is 1, and here the factor is xy dashed minus y. Now, what was so special about this factor xy dashed minus y? Well, we discussed that particular function also, if you just recall earlier. So we'll say let I equal this factor xy dashed minus y, which comes from there. Right? Then, if you took di dx, okay, and we showed this earlier, and do a total derivative on I, we get 1 times y dashed plus xy double dashed minus y dashed, in which case we get xy double dashed. So that di dx equal to 0, and we showed all this before, implies xy double dashed equal to 0, and that implies that y double dashed equal to 0. And you may recall that if we have a non-trivial function I, for which di dx equal to 0 gives you an equation, then the function I is a first integral of the differential equation. So it turns out that this non-trivial factor we get up here, this non-trivial factor, coming from Euler operator on the Lagrangian equal to 0, is in fact a first integral for the very same equation. So here already there's a strong suggestion that there's a relationship between a first integral and a Lagrangian. And it essentially is summed up in this following theorem, which I'm not going to prove, but I'm going to state, an important theorem. So the theorem says the following. Let's suppose you have two Lagrangians. Suppose L and L1 or L dash are two Lagrangians, non-trivial, not equivalent, are alternative Lagrangians. Let me say are alternative Lagrangians for the same equation of some differential equation, and this time I'm going to write the differential equation as y double dashed equals e of xy y dashed. Let me write that a bit nicer. Here's the differential equation. Let's rather write it like this. xy y dashed xy y dashed y double dashed equal to 0. You've got two Lagrangians. That means E of L equal to 0 gives you this equation. E of L dashed equal to 0 gives you the same equation, but there may be factors before you conclude the equation. Right? So what we get is the following. Then this theorem says that the Euler operator on L dashed equal to 0 will give you the equation, but it actually equals some function I, function of xy y dashed, times the Euler operator on the other Lagrangian, where you can actually compute this I in a slightly different way, where this function I is equal to the second derivative of L1 or L dashed, with respect to y dashed divided by the second derivative of L with respect to y dashed. So it's a ratio of these two second derivatives. Moreover, this function I is in fact a first integral, and I is a first integral of the differential equation. Of the given differential equation. Equal to 0. The differential equation we had earlier on. And another theorem, it's not a it's not the reverse of this, but it's a theorem that works slightly differently. In this theorem I just stated, you are given two Lagrangians of the same equation, you construct a first integral. This theorem says, suppose you have a Lagrangian and a first integral. So in this case, if L is a Lagrangian of a differential equation and I is a first integral, that means you have a conservation law of some equation, let's say the differential equation e of x, y dashed, y double dashed equal to 0, then we can construct an alternative Lagrangian. Then there exists L star, say, an alternative Lagrangian to the same equation. So you can construct new Lagrangians, an alternative Lagrangian of the same equation. So the whole idea here is, in the second theorem, that if you have a Lagrangian, if you have a first integral, you can construct a new Lagrangian, and so on and so on. In the work that comes here on, we will eventually prove a very powerful theorem that shows how we can construct these conservation laws, these first integrals from the Lagrangians, but more importantly, the invariance properties of that Lagrangian.